Hello, I'm Christophe.
And I'm Konstantin.
Today, we would like to tell you more about our unique approach to quantum error correction and fault-tolerant quantum computing. Our approach is unlike any other because we take advantage of the redundant encoding that is at the foundation of the ParityQC architecture, while also leveraging hardware features such as noise bias with a co-design strategy.
Quantum error correction protects fragile quantum states by encoding information into logical qubits built from many physical qubits. However, this protection comes at a cost. It introduces significant space and time overhead. The key challenge here is develop efficient code and decoders that minimize this overhead.
The most established option today is the surface code. It can handle a relatively high error level of noise with only local interaction on the plane and is suitable for fast decoding. But it demands a very large number of qubits and a costly routing of quantum information across the chip.
More recently, new families of quantum error correcting code have emerged. They aim to reduce this overhead and scale more efficiently by spreading information in more compact ways. However, significant technological challenges remain before we can implement this in real hardware. The main challenge here include long-range qubit connectivity, increased complexity of logical gates, and harder decoding problems.
Our Parity Code takes a different approach. Instead of adding qubits that only provide redundancy, it introduces parity qubits that also participate in the logical computation. These qubits store parity information, which is a combined state of several logical qubits. And by acting on a single parity qubit, logical entangling gate can be implemented directly.
To achieve all-to-all logical connectivity, we design a parity qubit for each pair of logical qubits. We call it the parity encoding. Here, any two logical qubits can be entangled using only local operations on the chip. Even better, as we show in our recent paper, the redundant encoding of this layout allows for a very efficient decoding. Errors can be identified and corrected with smart classical algorithms. The Parity Code is essentially a classical code capable of correcting only one type of error. So in order to provide full error protection, it must either be used with noise-biased qubits, such as cat qubits, or be combined with an additional layer of encoding.
But the design is highly flexible. You can build layout where parity qubits encode larger group of logical qubits, allowing multi-qubit entangling gates and optimizing resource for more complex algorithms. Using a technique called curve deformation, we can create transition between different layouts in constant time, which means that the code can be adapted on the fly to the need of the algorithm. So, as we've seen, quantum error correction is one of the central challenges for scaling quantum computers. And with the Parity Code, it is clear that clever code design, matched to hardware, can lead to scalable, fault-tolerant quantum computers.
Thank you very much for watching. If you would like to learn more about our path to full fault tolerance, you can read our recent papers or follow our future developments.